Hey everyone, welcome to this explainer. Look, if you've ever sat in a crowded, high-pressure lecture hall, just staring at a whiteboard full of squiggly lines and Greek letters, feeling that absolute wave of panic wash over you, well, take a deep breath, you are exactly in the right place. Today, we're taking a super calm, highly structured approach to understanding basic electrical engineering. No stress, no rushing, just you, me, and a few really clear concepts to help us transform what looks like absolute chaos into crystal clarity.
So how do engineers actually make sense of seemingly chaotic electrical circuits? It's a completely genuine question, right? Because, let's be honest, at first glance, a complex circuit diagram looks an awful lot like an intimidating bowl of metallic spaghetti. It feels totally erratic. But you know what's really interesting about this? Those tangled webs aren't chaotic at all. Not even a little bit. They're actually just basic logical puzzles. And like any good puzzle, they're governed by a few very strict, highly predictable rules. Once you know the rules, poof, the chaos simply vanishes.
So here's our low-pressure roadmap for today. First, we'll uncover the invisible foundations. Second, the pieces of the puzzle. Third, the rules of the road. And finally, simplification superpowers. All right, let's get right into it.
Step 1. The invisible foundations. We're going to start right at the bottom with the fundamental building blocks of electricity.
Before we can possibly analyze an entire electrical system, we logically need to define the absolute smallest invisible forces at play. I mean, you can't build a house without understanding the bricks, right? Well, the very first brick is electric charge. Charge is simply the characteristic property of tiny particles. So we've got protons carrying a positive charge and electrons carrying a negative charge. And we measure this in a unit called coulombs. The really crucial point here is to remember that charge isn't some mystical, magical force. It's literally just a physical property of the microscopic particles running through our devices.
Now, what happens when those little charges actually start moving? Well, that brings us to electric current. Current is simply the rate of flow of that electric charge over time. In a textbook, you'll often see it written out mathematically as I equals dq over dt. But hey, mathematical jargon aside, just picture a calm, steady stream of water flowing through a pipe. That flow, that's your current. And we measure that flow in amperes.
But water doesn't just magically flow on its own, does it? It needs pressure. It needs a pump. In an electrical circuit, that pump is electrical potential, or as we much more commonly call it, voltage. Voltage is the amount of work to be done to physically move a unit of positive charge from one place to another. Measured in volts, you can think of it as the pressure that actively pushes our current right through the system.
Okay, moving on to section 2. The pieces of the puzzle. Now we need to categorize the physical components that those invisible forces actually flow through. All right, so we've got our invisible forces down: charge, current, and voltage. When you're analyzing a circuit board, sure, there are hundreds of little pieces, but we can actually divide the entire world of components into just two really simple categories: active elements and passive elements. Honestly, it's all about energy. Active elements are the givers. They supply energy to the circuit. Think of your everyday batteries, your voltage sources, and your current sources. Passive elements, on the other hand, well, they're the takers, or sometimes the hoarders. They either dissipate energy, like a resistor, or they temporarily store it up, like an inductor or capacitor.
We can also sort these puzzle pieces by how they behave. We've got linear elements and nonlinear elements. Linear components, like resistors, are your incredibly reliable rule followers. They satisfy Ohm's law perfectly. So if you increase the voltage, the current increases in a direct, completely predictable straight line. Nonlinear elements, like diodes, they are the rebels. They simply don't follow a straight line relationship. By organizing these components into neat, predictable behavioral boxes, suddenly that crazy spaghetti bowl is already starting to look like a highly organized system.
That brings us to section 3, the rules of the road. Let's introduce Kirchhoff's laws. So we have our moving forces and our puzzle pieces. Now what actually happens when we connect them all together? Well, we need some traffic rules. Just picture a perfectly balanced four-way traffic intersection. This perfectly illustrates Kirchhoff's current law, or KCL. It's essentially a junction rule. It states that the algebraic sum of the currents meeting at a node, or a junction, is exactly 0. Basically, the number of cars entering the intersection absolutely must equal the number of cars leaving it. No cars are just magically vanishing into thin air here. Simply put, what goes in must come out.
And right alongside that is its counterpart, Kirchhoff's voltage law, or KVL. This one is the loop rule. If you virtually walk a complete circle around a closed circuit loop, the algebraic sum of the voltages has to be 0.
So the total energy supplied to the loop by your active elements perfectly equals the total energy dropped or consumed by your passive elements. It creates this incredibly beautiful, mathematically perfectly balanced loop.
Finally, we've arrived at Section 4, Simplification Superpowers. Let's take a look at Thevenin's theorem.
Here's the thing. Even when you know all the rules, sometimes a circuit is just way too big. It's got too many loops, way too many nodes, and honestly, it can feel totally exhausting. That is exactly why engineers developed a brilliant method to turn a massive, complex network into a tiny, simple one. The crucial point of Thevenin's theorem is this. It states that literally any two-terminal linear network, no matter how ridiculously complicated it is, can be completely replaced by an equivalent circuit that consists of just two things. A single voltage source, which we call V Thevenin, in series with a single resistor called R Thevenin. It's essentially an engineer's ultimate magic trick. You cover up the chaotic part of the circuit, wave a wand, and replace the whole shebang with just one battery and one resistor.
I know, it might sound like complex magic, but we can actually break it down into a super simple, low-stress, three-step baking recipe. Step 1. You temporarily disconnect the load. That's just the part of the circuit you're actually interested in. Step 2, you find VTH, which is simply the open circuited voltage across those exact terminals you just freed up. And step 3, you find RTH, which is the equivalent resistance of the network looking back into those terminals. You just follow the recipe and the chaos disappears.
By calmly applying our 3 steps, removing the load, calculating the open circuit voltage, and finding the equivalent resistance, we can completely collapse a really messy, tangled architecture of multiple resistors and branches into a neat, clean, two-piece equivalent. It's pretty amazing when you see it happen.
You know, I absolutely love this direct quote from the source textbook because it perfectly summarizes the underlying philosophy of everything we've talked about today. It says, these theorems reduce a complex network, as seen from two terminals, into a simple circuit so that its responses can be easily determined. It is all about reduction. It's about not letting the sheer volume of information completely overwhelm you, and instead systematically reducing it down to what actually matters.
And that brings us to our final thought for this explainer. At its heart, whether we're talking about electrical currents or just life's everyday challenges, engineering is simply breaking big, intimidating problems into small, perfectly manageable pieces. We went from a chaotic bowl of spaghetti to a beautifully simple, highly logical system just by identifying the foundations, categorizing the parts, and applying the rules. So I'll leave you with this question to ponder. What complex, seemingly chaotic problem in your own life can you simplify next? Thanks so much for learning with me today.